let me tell you about a squash court. Not a glamorous place, right? Just a small enclosed room where people hit a rubber ball against the walls. But there was one particular squash court underneath the west stands of Stagg Field at the University of Chicago that became arguably the most important room in the 20th century. On December 2nd, 1942, a team of scientists and engineers gathered there, some of them standing on a balcony looking down, and they watched a quiet, thin, Italian-born physicist named Enrico Fermi calmly give instructions to pull out a control rod, one notch at a time, from a massive pile of graphite and uranium that filled most of the room. And as that rod came out, click by click, the neutron counters began to climb. Slowly at first, then steadily, then unmistakably. For the first time in human history, a self-sustaining nuclear chain reaction was happening. Not in a star, not in the heart of the Earth, but in a structure that people had built with their own hands, brick by careful brick. There was no explosion, no dramatic flash of light. The pile. They literally called it a pile, Chicago Pile 1, because that's essentially what it was, a carefully stacked pile of blocks. It just sat there, quietly generating heat, while the instruments clicked faster and faster. Fermi watched the readings, did some calculations on his slide rule, and after about 28 minutes he told them to put the control rod back in. And that was it. He smiled, and someone handed him a bottle of Chianti, and they passed around paper cups, and they drank a toast. No labels on the bottle, no speeches. Just a group of exhausted, brilliant people who knew they had just changed everything. But here's the thing. That moment didn't come out of nowhere. It was the result of an extraordinary chain of discoveries, arguments, accidents, and insights that stretched back decades, involving some of the most fascinating minds who ever lived. And Fermi himself, the man at the center of it all, had a story that's almost too unlikely to be true. So let's start there. Let's start with who this person was, because understanding him is the key to understanding how that pile came to exist. Enrico Fermi was born in Rome on September 29, 1901. His father, Alberto, worked for the Italian railway system, and his mother, Ida, was a school teacher. They were not wealthy. They were not connected to any scientific tradition. There was nothing about his family background that would predict what he became. But from a very early age, Enrico was different in a way that's hard to overstate. He didn't just like math and science. He consumed them the way other kids consumed adventure novels. When he was about 10 years old, his older brother Giulio, who was his closest companion, died suddenly during a minor surgical procedure. It was devastating for the family, and especially for young Enrico. Some biographers think that this loss drove him even deeper into the world of books and ideas, a place where things made sense, where you could find order. By the time he was a teenager, he was buying used physics textbooks from the open-air market at Campo de' Fiori in Rome. And these weren't introductory texts. He found a book from 1840, written in Latin, called Elementorum Physicae Mathematicae, and he read the whole thing, in Latin, at 14. When he finished it, he reportedly told a friend that he hadn't even noticed it wasn't in Italian. That's the kind of mind we're talking about. Not just smart, absorbed. Completely, utterly absorbed. He went to the Scuola Normale Superiore in Pisa at 17, and within a few years, his professors essentially admitted that he knew more physics than they did. His doctoral thesis was on X-ray diffraction, and by the time he defended it in 1922, he was already thinking about problems at the frontier of what was then a brand new field, quantum mechanics. And here's what made Fermi truly unusual. what set him apart from nearly every other physicist of his era. He was both a theorist and an experimentalist. That almost never happens. Typically, you're one or the other. The theorists work with equations and models, and the experimentalists work with equipment and measurements. And they respect each other, but they live in different worlds. Fermi moved between both worlds effortlessly. He could derive the mathematics of a nuclear process in the morning, and then go into the lab in the afternoon and build the apparatus to test it. His colleagues called him the Pope, partly as a joke about his authority, but also because when Fermi said something was true, it usually was. He had this uncanny physical intuition that let him estimate answers to complex problems with startling accuracy, often before anyone had done the detailed calculation. Now, to understand what Fermi eventually built in that squash court, you need to understand the discoveries that made it possible. And that means we need to talk about what was happening in physics in the early 20th century, because it was one of the most extraordinary periods of discovery in human history. Just wild, revolutionary stuff happening almost every year. It starts, really, with radioactivity. In 1896, Henri Becquerel in Paris accidentally discovered that uranium salts could fog a photographic plate even when it was wrapped in black paper. Something was coming out of the uranium, some kind of invisible ray, and it had nothing to do with sunlight or any external energy source. The uranium was just emitting something, all on its own. Marie and Pierre Curie followed up on this, isolating new radioactive elements, polonium and radium, and showing that radioactivity was a property of certain atoms themselves. This was shocking. For centuries, atoms had been thought of as tiny, indivisible, unchanging billiard balls. And now here they were, spontaneously spitting out energy. Something was happening inside them. Then in 1911, Ernest Rutherford, a New Zealander working in Manchester, England, performed one of the most beautiful experiments in the history of science. He had his students fire tiny alpha particles, which are basically helium nuclei, little positively charged bullets, at a thin sheet of gold foil. Most of the particles went straight through, which was expected, but a few of them bounced back at sharp angles. Some came almost straight back toward the source. Rutherford said it was as if you'd fired a cannon shell at tissue paper, and it came back and hit you. The only explanation was that most of the atom was empty space, but at its center was a tiny, incredibly dense, positively charged core, the nucleus. And just like that, the picture of the atom changed forever. It wasn't a solid little ball. It was mostly nothing, with a tiny, heavy heart. Now think about what that means. All the mass of an atom, essentially all of it, is concentrated in this nucleus that's about 100,000 times smaller than the atom itself. If an atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. And yet that marble contains almost all the weight. The density is almost incomprehensible. A teaspoon of pure nuclear matter would weigh something like 1 billion tons. That's not a metaphor. That's roughly accurate. So physicists in the 19-teens and 20s knew that there was an enormous amount of energy locked up inside atomic nuclei. They could see it leaking out in radioactive decay. Uranium and radium slowly releasing energy over time. But they had no way to get at it in any controlled or useful fashion. It was like knowing there was a vast reservoir of water behind a dam, but having no valve to open. Rutherford himself, as late as 1933, called the idea of extracting useful energy from atoms moonshine. He didn't think it could be done. But here's what's really clever about how the next piece fell into place. In 1932, James Chadwick, who was working in Rutherford's lab at Cambridge, discovered the neutron. This was huge. People had known about protons, the positively charged particles in the nucleus, for years, and they'd known about electrons orbiting outside. But the math didn't add up. Nuclei were heavier than the protons alone could account for. Chadwick showed that there was another particle in there, about the same mass as a proton but with no electric charge. Neutral. The neutron. And this is where it gets interesting for our story, because the neutron turned out to be the key to everything. See, if you want to mess with an atomic nucleus, you have a problem. The nucleus is positively charged because of all those protons. So if you try to fire a positively charged particle at it, like an alpha particle or a proton, the nucleus repels it. It's like trying to push two magnets together with the same poles facing each other. You need tremendous energy to overcome that electrical repulsion and actually hit the nucleus. But a neutron? A neutron has no charge. It doesn't feel that repulsion at all. You can send a neutron drifting toward a nucleus at any speed, even very slowly, and the nucleus won't push it away. It'll just absorb it, like a ball rolling into a hole. No resistance. Fermi grasped this immediately. Almost as soon as Chadwick announced the neutron's discovery, Fermi began thinking about what you could do with it. And by 1934, he and his group in Rome, a brilliant team that included Emilio Segre, Eduardo Amaldi, Franco Rossetti, and Oscar D'Agostino, were systematically bombarding every element they could get their hands on with neutrons. They'd take a neutron source, typically a small amount of radon mixed with beryllium powder, which produces neutrons through a nuclear reaction, and they'd place it next to samples of different elements and see what happened. They worked their way through the periodic table, element by element, like explorers mapping a new continent. And they found something remarkable. When neutrons hit certain elements, those elements became radioactive. The neutron would be absorbed into the nucleus, making it unstable, and then it would decay, emitting radiation. Fermi's group discovered dozens of new radioactive isotopes this way. It was an incredibly productive period. They were making discoveries so fast that they sometimes published several papers in a single week. But then came the really strange part. One day in October of 1934, they noticed something they couldn't explain. They were bombarding silver with neutrons, and the results were inconsistent. Sometimes the silver became very radioactive, and sometimes it didn't, and they couldn't figure out what was different. Fermi had a hunch. He decided to put a block of paraffin wax between the neutron source and the silver target. Now, this was a weird thing to do. You'd think that putting a barrier in the way would reduce the effect, right? Block some of the neutrons. But Fermi had this instinct, this physical intuition that his colleagues marveled at. And when they put the paraffin in place, the radioactivity of the silver didn't decrease. It increased, dramatically, by a factor of 100 or more. Fermi went home for lunch. This was Italy after all, and lunch was sacred, and he spent the meal thinking furiously. By the time he came back to the lab, he had the answer. The paraffin was full of hydrogen atoms, which have nuclei that are almost exactly the same mass as a neutron. When a neutron hits a hydrogen nucleus, it's like a billiard ball hitting another billiard ball head-on. It transfers almost all of its energy. So the neutrons were bouncing around inside the paraffin, colliding with hydrogen nuclei, losing energy with each collision, slowing way down. And these slow neutrons, it turned out, were far more effective at being captured by other nuclei than fast ones were. It seems counterintuitive. You'd think a faster bullet would be more effective, but in the quantum world, a slower neutron spends more time near the nucleus, and that gives it a higher probability of being absorbed. Fermi worked out the theory that same afternoon. This discovery, that slow neutrons are better at inducing nuclear reactions, would turn out to be absolutely critical for everything that followed. It's one of those insights that seems simple in hindsight, but changed the entire trajectory of nuclear physics. And it happened because Fermi trusted his gut and tried something that didn't seem to make logical sense. That combination of rigorous theory and bold experimental instinct, that was Fermi's genius. Now, during these experiments in Rome, Fermi's group did something else that they didn't fully understand at the time. When they bombarded uranium, element 92, the heaviest naturally occurring element, with neutrons, they got results that were confusing. They detected radioactive products that didn't match any known element near uranium on the periodic table. Fermi tentatively suggested they might have created new elements heavier than uranium, elements 93 and 94, which would be a spectacular discovery. The Italian press went wild. Mussolini's government loved it, Italian science conquering new frontiers. But privately, Fermi was cautious. He wasn't sure what was really happening, and as it turned out, the truth was far stranger and far more consequential than anyone imagined. Because what was actually happening inside those uranium nuclei when they absorbed a slow neutron wasn't the creation of a heavier element. It was something that no physicist had ever seriously considered possible. The uranium nucleus was splitting in two, and it would take 4 more years and scientists in 3 different countries before anyone figured that out. But when they did, it set off a chain of events that led directly to that squash court in Chicago and to the world we live in now. The person who finally put the puzzle together was not a physicist at all, at least not by training. Her name was Lise Meitner, and she was an Austrian-born physicist who had spent decades working in Berlin. And her story is one of the most remarkable and most unjust in the history of science. But to tell it properly, we need to go to Germany in the late 1930s, where the political situation was about to collide with nuclear physics in a way that changed everything. Germany in the late 1930s was a place where brilliance and cruelty existed side by side in a way that's hard to fully comprehend. The universities were still among the finest in the world. The tradition of German physics and chemistry stretched back generations. Names like Planck, Heisenberg, Einstein, Haber, Nernst. These institutions had produced Nobel laureates the way other countries produced wheat. But by the mid-30s, the Nazi regime had already driven out hundreds of Jewish scientists, dismantling what had been the most formidable scientific community on Earth. And Lise Meitner was caught right in the middle of that destruction. She had been born in Vienna in 1878, which makes her a full generation older than Fermi. Her father was a lawyer, and he was unusually progressive for the time. He insisted that all his daughters receive the same education as his sons. Lisa showed an early aptitude for mathematics and physics, but here's the thing. When she was growing up, women in Austria were not allowed to attend universities, not discouraged, not informally excluded, literally not permitted. She had to wait until the rules changed in 1901, and then she enrolled at the University of Vienna, where she studied under Ludwig Boltzmann, one of the founders of statistical mechanics. Boltzmann was a towering figure, passionate and intense, and he apparently made a deep impression on the young Meitner. She got her doctorate in 1906, only the second woman to earn a physics doctorate from Vienna. And then she did something brave. She moved to Berlin. She wanted to work at the frontier of physics, and Berlin was where the frontier was. She attended Max Planck's lectures. Planck, who had launched the quantum revolution just a few years earlier. And she began a collaboration with a chemist named Otto Hahn that would last, off and on, for over 30 years. Now, Hahn was a gifted radiochemist, meticulous and skilled at separating and identifying chemical elements. Meitner was the physicist, the one who understood the theory, who could interpret what the experiments meant in terms of what was happening inside the atom. They were a perfect complement to each other, and they knew it. But the conditions Meitner worked under were absurd. When she first arrived in Berlin, she wasn't allowed to enter the main chemistry building because she was a woman. She worked in a converted carpenter's workshop in the basement. She had no official position, no salary. For years, she worked essentially as a volunteer, sustained by a small allowance from her family. Think about that for a second. One of the most talented physicists of her generation, working in a basement, unpaid, because the institution couldn't handle the idea of a woman in the laboratory. And yet she persisted. She published important papers. She earned respect from her peers, slowly, grudgingly. During the First World War, she served as an X-ray technician on the Austrian front, then returned to Berlin, and eventually, finally, got a proper academic position. By the 1920s, she was a respected professor, head of her own physics section at the Kaiser Wilhelm Institute. She and Hahn continued their partnership, studying radioactive elements, refining techniques for identifying isotopes. So when Fermi's results from Rome arrived in Berlin in 1934, those puzzling experiments where neutrons were fired at uranium and produced mysterious radioactive products, Meitner and Hahn were among the best-equipped scientists in the world to investigate further. They teamed up with a younger chemist named Fritz Strassmann, and together, the three of them began a careful, systematic study of what happened when uranium was bombarded with neutrons. This work went on for 4 years. 4 years of painstaking chemistry and careful measurement, trying to identify exactly what elements were being produced. And here's where the politics collide with the physics. In March 1938, Nazi Germany annexed Austria. Overnight, Lise Meitner, who had been an Austrian citizen, became a German citizen under Nazi law. And under Nazi law, she was Jewish. She had actually converted to Protestantism decades earlier, but that didn't matter to the Nazis. Their racial laws were based on ancestry, not belief. Suddenly, Meitner was in serious danger. She had been somewhat protected before because she was an Austrian national, but that protection evaporated with the Anschluss. Friends and colleagues scrambled to help her escape. In July 1938, she fled Germany with almost nothing. She later said she left with 10 marks in her purse. She made it to the Netherlands with the help of a Dutch physicist named Dirk Koster, who met her at the border and essentially talked her past the guards. From there, she eventually made her way to Sweden, where she took a position at the Nobel Institute in Stockholm. But it was a lonely, underfunded position, and she was cut off from the laboratory, the equipment, and the collaboration that had defined her working life. Meanwhile, back in Berlin, Hahn and Strassmann kept working. And in December 1938, just a few months after Meitner's escape, they made a discovery that baffled them. They had been bombarding uranium with neutrons, carefully separating the products using standard radiochemistry techniques. And they kept finding barium. Barium, element 56. That made no sense. Barium has an atomic number roughly half that of uranium. If you're bombarding uranium with neutrons, you might expect to find elements near uranium on the periodic table. Elements 89, 90, 91, maybe even 93 or 94, as Fermi had suggested. But barium, that was like throwing a pebble at a boulder and having the boulder split clean in half. There was no known nuclear process that could explain it. Hahn was a superb chemist, and he trusted his results. He had identified barium beyond any reasonable doubt, but he couldn't explain it. He wrote to Meitner in Sweden, describing the findings, and his letter essentially said, "We know it's barium, but we can't understand how. Can you think of any explanation?" And this is one of those moments in the history of science that gives you chills if you sit with it long enough. Meitner received Hahn's letter just before Christmas, 1938. She was visiting friends in the small Swedish town of Kungälv, near Gothenburg. Her nephew, Otto Robert Frisch, who was also a physicist and had also fled the Nazis, he was working in Copenhagen with Niels Bohr, came to visit her for the holidays. And on a walk through the snowy Swedish countryside, aunt and nephew sat down on a fallen tree trunk and worked out, on scraps of paper, the physics of what Hahn and Strassmann had observed. Here's what Meitner realized. She thought about the nucleus not as a rigid, solid sphere, but as something more like a liquid drop, an idea that Bohr himself had been developing. If you think of the uranium nucleus as a big, wobbly drop of liquid, held together by the nuclear strong force but also pushed apart by the electrical repulsion of all those protons, 92 protons, all positively charged, all repelling each other, then the nucleus is already in a precarious state. It's like an overfull water balloon. Now, if a neutron comes in and is absorbed, it adds energy to this already unstable drop. The drop starts to oscillate, to stretch and wobble. And if the oscillation is large enough, the drop can elongate into a dumbbell shape, and then the electrical repulsion between the two halves overwhelms the nuclear force trying to hold them together, and the drop splits in two. Two smaller nuclei fly apart with tremendous energy. Meitner and Frisch calculated the energy release using Einstein's famous equation, E equals mc squared. They looked at the masses of the original uranium, nucleus and the two fragment nuclei, and they found that the fragments together weighed slightly less than the original. That missing mass, a tiny amount, but real, had been converted into energy. And when they did the arithmetic, the energy released by a single uranium nucleus splitting was enormous by atomic standards, about 200 million electron volts. For comparison, a typical chemical reaction, burning coal, say, releases a few electron volts per atom. So nuclear fission, as Frisch would soon name it, borrowing the term from biology, where cells divide by fission, released roughly 100 million times more energy per atom than any chemical reaction. Let that sink in for a moment. 100 million times more, from a single atom of uranium. Frisch rushed back to Copenhagen and told Bohr, who was about to leave for a trip to the United States. The story goes that Bohr smacked his forehead and said something like, "Oh, what fools we have been. We should have seen this before." And he was right. In retrospect, the clues had been there for years. Fermi's confusing results in Rome, the anomalous findings from Irène Joliot-Curie in Paris, who had also detected unexpected light elements among the products of uranium bombardment, All of it pointed to fission, but nobody had made the conceptual leap because it seemed too outrageous. The idea that a nucleus could simply break apart like that was so far outside the existing framework of nuclear physics that even the best minds in the world hadn't considered it. Bohr arrived in New York in January 1939 and almost immediately shared the news with American physicists. The effect was electric. Within weeks, laboratories across the United States had confirmed fission experimentally. It was remarkably easy to reproduce. You just needed a neutron source and some uranium, and you could see the enormous energy pulses on your instruments. The physics community was buzzing, and almost immediately, people began asking the obvious next question. The question that would change everything. When a uranium nucleus splits, it produces two large fragment nuclei. But uranium has 92 protons and about 146 neutrons. That's a lot of neutrons. The two fragment nuclei don't need all of those neutrons. So what happens to the extras? Do additional free neutrons get released during fission? Because if they do, if each fission event releases 1 or 2 or 3 free neutrons, then those neutrons could go on to strike other uranium nuclei, causing more fissions, releasing more neutrons, which cause still more fissions. A chain reaction. And if you could sustain that chain reaction, you would have a source of energy unlike anything the world had ever seen. Or, if the chain reaction happened fast enough in a concentrated enough mass of uranium, you would have a bomb of unimaginable power. This was early 1939. Europe was sliding toward war. Hitler had already taken Austria and Czechoslovakia. And suddenly, physicists, many of them refugees from fascism themselves, realized that the basic science for an atomic weapon was sitting right there in the open literature, available to anyone, including German scientists who were perfectly capable of understanding it. The race, though nobody used that word yet, had already begun. And one of the physicists who grasped the implications most quickly, who understood both the science and the engineering challenges that would need to be solved, was that same Italian émigré who had unknowingly split uranium atoms 4 years earlier in Rome and was now living in New York, having just accepted a professorship at Columbia University. Enrico Fermi had left Italy in December 1938, the same month Hahn and Strassmann discovered barium, traveling to Stockholm to accept his Nobel Prize, and then simply never going back. His wife Laura was Jewish, and Mussolini's government had recently adopted racial laws modeled on the Nazi ones. So Fermi collected his Nobel, boarded a ship with his family, and sailed to America. And within weeks of arriving, he heard about fission, and he immediately began thinking about neutrons, specifically about whether a chain reaction was actually possible. And the very first thing he needed to know, the absolutely essential piece of information before anything else mattered, was how many neutrons come out of a single fission event. Because think about it this way. If you split a uranium nucleus and it releases energy but only 1 neutron, or worse, no neutrons at all, then the whole chain reaction idea is dead on arrival. You need that one fission to trigger at least one more fission, and ideally more than one, because in practice you're always going to lose some neutrons. They'll escape out the sides of whatever material you're working with. They'll get absorbed by impurities or by uranium atoms that capture them without actually splitting. So the real question isn't just, do neutrons come out? It's, do enough neutrons come out to overcome all the losses? Fermi started working on this at Columbia in January 1939, almost immediately after hearing about fission. And he wasn't alone. Across the Atlantic, Frédéric Joliot-Curie in Paris, the son-in-law of Marie Curie, which gives you a sense of how small this world still was asking exactly the same question. So was Leo Szilard, a Hungarian physicist who had actually patented the idea of a nuclear chain reaction back in 1933, years before fission was even discovered. Szilard was a fascinating character, one of those people who seems to show up at every critical moment in 20th century physics. He had fled Berlin in 1933, literally the day after the Reichstag fire, because he had a habit of reading political situations correctly and acting before everyone else. He'd been living in hotel rooms ever since, carrying his belongings in 2 suitcases, working at various institutions, and thinking obsessively about chain reactions. When fission was announced, Szilard immediately understood the implications, and he rushed to Columbia to find Fermi. Now, here's something interesting about the Fermi-Szilard relationship. They were very different people. Fermi was methodical, careful, almost conservative in his scientific claims. He liked to work through problems step by step, building up from solid foundations. Szilard was more of a visionary, brilliant, impatient, full of ideas, not always interested in the painstaking experimental work needed to prove them. Fermi found Szilard somewhat irritating. Szilard found Fermi somewhat cautious, but they needed each other. Szilard had the theoretical insight and the political urgency. Fermi had the experimental genius and the ability to actually build things and make measurements. Together, along with other physicists at Columbia like Herbert Anderson and Walter Zinn, they set about answering the neutron question. The experiments they ran in early 1939 were elegant in their simplicity. You take a source of neutrons, you direct them at uranium, and you set up detectors around the uranium to count how many neutrons come flying out after fission occurs. The tricky part is distinguishing the neutrons produced by fission from all the other neutrons bouncing around. But Fermi was a master of this kind of careful measurement. By March 1939, both the Columbia group and Joliot-Curie's group in Paris had their answer, and it was the answer that changed everything. Each uranium fission event releases, on average, about 2 to 3 secondary neutrons. The Columbia group measured roughly 2. The Paris group got about 3.5, which turned out to be a bit high, but the point was the same. The number was greater than 1, significantly greater than 1. And that meant a chain reaction was, at least in principle, possible. Now, in principle is doing a lot of heavy lifting in that sentence, because the gap between in principle, a chain reaction could work, and we have actually built a functioning nuclear reactor, is enormous. It's like saying, in principle, you could walk from New York to Los Angeles. Sure, technically, your legs work, the road exists. But there are about 10,000 practical problems between you and the Pacific Ocean. And Fermi understood this better than almost anyone, because he was the rare physicist who thought like an engineer. He didn't just care about whether the physics allowed it, he cared about how you would actually do it. So let's talk about the problems. The first and biggest one was something called the multiplication factor, which physicists denoted with the letter K. This is the number that tells you whether your chain reaction will sustain itself. If K equals exactly 1, it means that for every generation of fissions, you get exactly as many fissions in the next generation. The reaction is self-sustaining. It keeps going at a steady rate. If K is greater than 1, the reaction grows. Each generation produces more fissions than the last. If K is less than 1, the reaction dies out. Every generation produces fewer fissions, and eventually the whole thing fizzles. To build a reactor, Fermi needed K to be at least 1, and getting there required solving a whole cascade of interconnected problems. Let me walk you through the main ones, because they're genuinely fascinating from an engineering standpoint. First, There's the issue of which uranium atoms actually undergo fission. Natural uranium, the stuff you dig out of the ground, is a mixture of two isotopes. About 99.3% of it is uranium-238, and only about 0.7% is uranium-235. Here's the thing. It's the rare isotope, U-235, that fissions easily when hit by a slow neutron. U-238 is much more stubborn. It tends to simply absorb neutrons without splitting, especially neutrons in a certain intermediate energy range. It captures them and becomes uranium-239, which eventually decays into plutonium. But that's a story for later. The point is that U-238 is, from the chain reaction perspective, mostly a neutron sink. It eats your neutrons without giving you anything useful in return, at least not immediately. So you've got this material that's 99.3% neutron absorber and 0.7% fuel. That's a terrible ratio. It's like trying to start a campfire where 99% of your wood is wet and only 1% is dry kindling. You can see why getting K above 1 was going to be incredibly difficult. There were two possible approaches to this problem. The first was isotope separation, physically sorting out the U-235 from the U-238 and concentrating the fissile material. But in 1939, nobody had any practical method for doing this on a meaningful scale. The two isotopes are chemically identical. They're both uranium. They behave the same way in chemical reactions. The only difference is that U-235 atoms are slightly lighter, by about 1.3%. Separating them requires exploiting that tiny mass difference through physical processes like gaseous diffusion or centrifugation. And in 1939, these techniques were either theoretical or could produce only microscopic quantities. Isotope separation would eventually become a massive industrial effort. Entire cities would be built around it. But in early 1939, it wasn't a practical option. The second approach was the one Fermi pursued. Use natural uranium with all its U-238, but slow the neutrons down so much that they become what physicists call thermal neutrons. Here's why this matters. When a neutron is first released by fission, it's moving incredibly fast, about 20,000 kilometers per second. At that speed, it has a relatively low probability of causing another U-235 atom to fission. But if you can slow that neutron way down to about 2 kilometers per second, which corresponds to the thermal energy of room temperature atoms, its probability of causing fission in U-235 increases enormously, by a factor of hundreds. The physics behind this is quantum mechanical and has to do with resonance cross-sections, but the intuition is almost like the difference between throwing a ball past someone versus rolling it gently toward them. The slow ball is much easier to catch, but here's the catch. And this is where the engineering gets really clever and really tricky. You can't just mix the uranium and the slowing down material together randomly, because as the neutrons are slowing down, they pass through that intermediate energy range where U-238 is extremely good at absorbing them. There are specific energies, called resonance energies, where U-238's appetite for neutrons is voracious. If a neutron happens to be at one of those energies when it encounters a U-238 atom, it gets swallowed up almost certainly. Gone. Lost to the chain reaction. So Fermi needed a moderator, a material that would slow the neutrons down, and he needed to arrange the uranium and the moderator in a geometry that would minimize the chances of neutrons being captured by U-238 during the slowing down process. The solution he came up with was to separate the uranium and the moderator into distinct regions. Instead of mixing them together homogeneously, you embed lumps of uranium in a matrix of moderator material. The neutrons are born fast inside the uranium lumps. They escape into the moderator. They bounce around and slow down in the moderator, which is chosen to be a material that slows neutrons efficiently without absorbing many. And by the time they wander back into another uranium lump, they've already been thermalized. They've already passed through the dangerous resonance energy range while they were safely in the moderator, away from the U-238. So they arrive at the next uranium lump already slow, already at the perfect energy to find a U-235 atom and cause another fission. It's a beautiful piece of physics reasoning, and the choice of moderator was critical. You need something with light atoms, because neutrons slow down most efficiently when they collide with atoms of similar mass, just like a billiard ball loses the most energy when it hits another billiard ball rather than a bowling ball. Hydrogen is the lightest element, so water seems like an obvious choice. But ordinary water has a problem. Hydrogen absorbs too many neutrons. Not a huge number, but enough to potentially kill your chain reaction when you're already struggling to get K above 1. There were two alternatives. One was heavy water. Water made with deuterium, the heavier isotope of hydrogen, instead of ordinary hydrogen. Deuterium is an excellent moderator. It slows neutrons almost as well as hydrogen, but absorbs far fewer. The problem was that heavy water was extraordinarily rare and expensive. In 1939, the entire world's supply of heavy water was maybe a few liters, mostly produced at a single plant in Norway, the Norsk hydro plant at Vemork, perched on a cliff above a waterfall in Telemark. That plant would later become the target of one of the most daring sabotage operations of the Second World War, but we'll get to that. The other alternative was graphite, pure carbon. Carbon atoms are heavier than hydrogen, so graphite isn't quite as efficient at slowing neutrons per collision. You need more of it, a thicker layer. But carbon absorbs very few neutrons, which means fewer losses. Fermi chose graphite. It was available, it was affordable, and the physics said it should work, provided the graphite was pure enough. And that word pure is about to become the most important word in this entire story, because the purity of the graphite would determine whether the whole project succeeded or failed. Here's why. Even tiny amounts of certain impurities in the graphite, we're talking parts per million, could absorb enough neutrons to drag K below 1. Boron, for instance, is a voracious neutron absorber. If your graphite contains even a few parts per million of boron, it can ruin everything. And commercial graphite in 1939 was not manufactured with nuclear purity in mind. It was made for electrodes, for crucibles, for industrial applications, where a few parts per million of boron meant absolutely nothing. Nobody had ever needed graphite this pure before, because nobody had ever tried to build a nuclear reactor before. Fermi and Szilard began approaching graphite manufacturers, companies like National Carbon Company and the Spear Carbon Company, and asking for the purest graphite they could produce. The manufacturers were puzzled. These physicists wanted graphite purer than anything that had ever been made, and they wouldn't fully explain why. This was already becoming a sensitive topic. Szilard, in particular, had been pushing hard for secrecy. He had convinced several physicists to voluntarily withhold their results on fission from publication, worried that German scientists would use the information. Not everyone agreed. Joliot-Curie in Paris published his neutron multiplication results, which infuriated Szilard, but the instinct towards secrecy was growing. So Fermi and his team at Columbia began a painstaking series of experiments in 1940 and 1941, stacking blocks of graphite and embedding pieces of uranium within them, measuring how neutrons behaved, calculating K for different arrangements. They called these experimental assemblies piles, a term Fermi used simply because they were, literally, piles of graphite bricks. The word stuck. For years afterward, nuclear reactors were called piles, long after they stopped looking anything like a pile of anything. The early results were not encouraging. The K values they measured were below 1, sometimes well below 1. The chain reaction was dying out, generation after generation of neutrons dwindling away. Fermi kept careful records, tracking every variable, the purity of the graphite, the arrangement of the uranium, the spacing between lumps. He was trying to optimize, to squeeze every last neutron out of the system. And slowly, agonizingly, the numbers started creeping upward. Better graphite helped, better geometry helped. Using uranium oxide pressed into dense lumps rather than spread out as powder helped, because it reduced the chances of resonance absorption. But the really dramatic improvement came when Fermi's team started getting access to metallic uranium instead of uranium oxide. Uranium metal is denser than the oxide, more uranium atoms packed into the same volume, which means neutrons born inside a metal lump are more likely to escape into the moderator before being captured by U-238. The metallurgy of uranium was itself a major challenge. Uranium is a difficult metal to work with. It's pyrophoric, meaning it can spontaneously catch fire in air, especially as a fine powder. Producing it in large, pure quantities required developing entirely new industrial processes. But by 1941, companies like Westinghouse and Metal Hydrides were beginning to produce uranium metal in meaningful amounts, and every new shipment gave Fermi's team better numbers. Meanwhile, the political and military context was accelerating everything. In August 1939, just before Germany invaded Poland, Albert Einstein had signed a letter to President Roosevelt, drafted largely by Szilard, warning that uranium chain reactions could potentially lead to extremely powerful bombs and that Germany might be pursuing this. The letter led, eventually, to the creation of the Advisory Committee on Uranium, which provided modest funding for fission research. But the effort was still small, still scattered across university laboratories, still moving at an academic pace. It wasn't until late 1941, after a critical report from the British MAUD Committee concluded that an atomic bomb was not only possible, but could potentially be built in time to affect the war, that the American program shifted into a completely different gear. And by then, Fermi had been stacking graphite and uranium for nearly 2 years, and he was getting tantalizingly close to the magic number. His latest measurements of K were approaching 0.9, then 0.95. The chain reaction was almost sustaining itself. Almost. He needed more material, purer material, and a bigger pile. And he was about to get all three, because in the summer of 1942, the entire project was reorganized under military control, given the codename the Manhattan Engineer District, and placed under the command of a driven, brilliant, sometimes ruthless Army colonel named Leslie Groves, who had just been promoted to brigadier general and was not at all happy about being assigned to a physics project when he wanted a combat command. Groves had just finished overseeing the construction of the Pentagon, the largest office building in the world, and he brought that same relentless build-it-now energy to the atomic bomb program. And one of the first things he did was make sure Fermi had everything he needed. Because Groves understood something that a lot of people in Washington hadn't fully grasped yet. You couldn't build an atomic bomb until you understood how a chain reaction actually behaved, and you couldn't understand how a chain reaction actually behaved until someone built a working reactor. Fermi's pile wasn't a sideshow, it was the foundation. Everything else, the bomb design, the plutonium production, the entire industrial apparatus that would eventually sprawl across 3 secret cities, all of it depended on whether a self-sustaining chain reaction could actually be achieved and controlled. So Groves cut through the bureaucratic tangles and suddenly Fermi had access to materials and resources that would have been unimaginable just months earlier. Now, Groves himself is worth pausing on for a moment, because he's one of those figures who doesn't get nearly enough attention in most tellings of this story. Leslie Richard Groves was born in 1896, the son of an army chaplain, and he grew up moving from post to post the way military kids do. He went to West Point, graduated 4th in his class, and became a Corps of Engineers officer, which in the Army means you're the person who actually builds things. Roads, bridges, airfields, fortifications. Groves had spent his entire career managing enormous construction projects, and he was extraordinarily good at it. He was also, by most accounts, difficult to work with, abrasive, impatient. He had a way of making decisions instantly and expecting everyone around him to keep up. The physicists found him overbearing. He found the physicists maddening. All their hedging, their on the other hand, their reluctance to commit to a timeline. But here's the thing about Groves. He got things done. And in wartime, that's what mattered. One of Groves's early decisions was to consolidate the reactor research. Fermi had been working at Columbia, but the project was being moved to the University of Chicago, where it would fall under a new organization called the Metallurgical Laboratory, the Met Lab, as everyone called it. The name was deliberately misleading. There was some metallurgy involved, sure, but the real purpose of the Met Lab was to figure out how to produce plutonium, a newly discovered element that was expected to be even more suitable for a bomb than uranium-235. And to produce plutonium, you needed a working reactor, because plutonium doesn't exist in nature in any meaningful quantity. It's created when uranium-238 absorbs a neutron and then undergoes a couple of beta decays. So the reactor wasn't just a scientific demonstration, it was a plutonium factory in embryo. Fermi arrived in Chicago in early 1942, and the work intensified immediately. The plan was to build a full-scale pile, what would become Chicago Pile 1, large enough to actually achieve a self-sustaining chain reaction. The original site was supposed to be a forested area called the Argonne Forest, about 20 miles southwest of the city. But construction there was delayed by a labor dispute, and Fermi, ever practical, ever impatient in his quiet way, suggested an alternative location that made some people very nervous. Underneath the west stands of Stagg Field, the university's old football stadium. The football team had been disbanded in 1939. The university's president, Robert Maynard Hutchins, thought college football was a distraction from academics, which gives you a sense of the kind of place the University of Chicago was. So the stadium was available, and it had a large squash court beneath the stands that was perfect for what Fermi needed, a big enclosed space with a high ceiling and a solid floor. Now think about what this means for a second. They were going to build the world's first nuclear reactor in the middle of a major American city, on a university campus, surrounded by neighborhoods, apartment buildings, families. If something went wrong, if the reaction got out of control, the consequences could be catastrophic. And there was no containment structure, no radiation shielding worth mentioning, no emergency cooling system. By any modern standard, this was insane. But Fermi was confident in his calculations, confident in his understanding of the physics, and confident in his ability to control what was about to happen. And honestly, his confidence was justified. Not because he was reckless, but because he was meticulous. He had been building toward this moment for years, measuring neutron multiplication factors in smaller and smaller increments, and he understood the behavior of this system better than anyone alive. The construction of Chicago Pile 1 began in November 1942. And when I say construction, I want you to picture something that looks nothing like what you probably imagine when you think of a nuclear reactor. There was no gleaming steel containment vessel, no cooling towers, no control room full of blinking lights. What there was a team of young physicists, many of them graduate students, stacking blocks, literally stacking blocks of graphite and uranium, layer by layer, like building an enormous, precise, very heavy brick structure. The pile was roughly spherical, about 25 feet wide and 20 feet high when it was finished, and it contained about 45,000 blocks of graphite, each one machined to precise dimensions. Some of those blocks had holes drilled in them to hold lumps of uranium metal, or uranium oxide. The whole thing weighed about 400 tons. The work was physically brutal. Graphite dust got everywhere, into their clothes, their skin, their lungs. The workers looked like coal miners by the end of each shift, covered head to toe in black dust, and they were working around the clock, in shifts, because the timeline was relentless. Groves wanted results. The war wasn't waiting. Here's what's really clever about how Fermi designed the pile. He didn't just stack everything up and hope for the best. He built it in layers, and after each layer was added, his team took careful measurements of the neutron activity inside the pile. They had instruments, ionization chambers and boron trifluoride counters, embedded at various points, and after each new layer of graphite and uranium was placed, they could measure how the neutron population was changing. This let Fermi track the multiplication factor K in real time as the pile grew. He could plot the curve and predict exactly how many more layers would be needed before K reached 1. It was like watching a pot of water slowly approach boiling. You could see the temperature climbing, and you could calculate when the bubbles would start. And there was a safety system, though calling it that might be generous by today's standards. The primary control mechanism was a set of cadmium-coated control rods, long strips of wood sheathed in cadmium, a metal that's extremely good at absorbing neutrons. When these rods were inserted into channels running through the pile, they soaked up enough neutrons to keep K well below 1. When you pulled them out, the neutron population could grow. So the basic idea was simple. Pull the rods out slowly, let K approach 1, and if anything goes wrong, shove them back in. There was also an emergency backup, a weighted rod called ZIP, which stood for something like Zone of Immediate Precipitation. Though honestly, the acronym might have been a backronym. ZIP was suspended above the pile by a rope, and if everything went sideways, someone could cut the rope with an axe and the rod would drop into the pile by gravity, shutting down the reaction. There was literally a physicist standing on a platform above the pile holding an axe. His name was Norman Hilberry, and his job was to be the last line of defense. Think about that. The safety system for the world's first nuclear reactor included a man with an axe. And then there was the suicide squad. That's what they actually called themselves, or at least that's what everyone else called them. This was a small group of men standing on top of the pile with buckets of cadmium sulfate solution. If the control rods failed and the axe failed, their job was to pour the liquid cadmium over the pile to flood it with neutron absorbers. It would have worked, probably, but it also would have meant these men were standing directly on top of an uncontrolled nuclear reaction, absorbing a potentially lethal dose of radiation. They volunteered for this. By early December, the pile was nearly complete. Fermi's measurements showed K creeping up through 0.95, 0.97, 0.99. Each new layer brought it closer. On December 1st, 1942, the team added the last layers, and Fermi's calculations showed that the pile was now large enough. If they withdrew the control rods far enough, the chain reaction would sustain itself. But it was getting late in the day, And Fermi, ever calm, ever methodical, decided they would stop for the night and finish the experiment the next morning. He wanted everyone rested. He wanted clear heads. Some of the younger physicists were practically vibrating with excitement, but Fermi just said it was time for dinner. So they covered the pile, locked the doors, and went home. And that night, in apartments and boarding houses across the south side of Chicago, several dozen people tried to sleep, knowing that tomorrow they were going to attempt something that had never been done before in the history of the world. Something that would either validate years of theory and painstaking work, or, in the worst case, the case nobody really wanted to think about too carefully. Something that could contaminate a significant portion of a city of 3 million people. The morning of December 2nd, 1942, was cold. Chicago in December usually is. The team gathered in the squash court beneath the west stands of Stagg Field, and the space was crowded, not just with the pile itself, which dominated the room, but with about 42 people who had come to witness the experiment. Some were scientists who had worked on the project. Others were officials from the Met Lab and the military. Arthur Compton was there. He was the Nobel laureate who ran the Met Lab. Szilard was there, of course. Herbert Anderson, Fermi's closest experimental collaborator, was there. And Fermi himself stood on the balcony overlooking the pile, calm and focused, directing the proceedings like a conductor leading an orchestra through a piece he had rehearsed 1,000 times. The experiment began methodically. Fermi ordered the control rods withdrawn in stages, a few inches at a time. After each withdrawal, the team would watch the neutron counters, listen to the clicking of the Geiger counters, the clicks coming faster and faster as the neutron population grew, and Fermi would calculate whether the reaction was self-sustaining or still subcritical. Each time, the neutron levels would rise, then plateau, still subcritical. Pull the rods out a little more, the levels rise again, plateau again. Fermi was checking his calculations against reality at every step, and reality was matching his predictions with an almost eerie precision. Every single step, the counters behaved exactly the way his calculations said they would. And that in itself was remarkable, because remember, nobody had ever done this before. There was no textbook for this. There was no precedent to check against. The only guide Fermi had was the physics itself, the math he had worked through on his slide rule and in his notebooks, and his own deep intuitive understanding of how neutrons move through matter. And so far, that understanding was proving flawless. Around mid-morning, something happened that could have been anticlimactic, but was actually kind of perfect. The automatic safety rod, the zip rod, the one held up by a rope that could be cut, tripped. It slammed down into the pile because the neutron intensity had reached the preset safety threshold. The counters had been climbing, and the automatic system did exactly what it was designed to do. It shut everything down. And Fermi, without any visible frustration, simply said something to the effect of, "Well, let's reset and start again." That's what they did. They reinserted the control rods, pulled out the zip rod, repositioned it, and began the slow process of withdrawal all over again. Then, right around lunchtime, Fermi did something that tells you a lot about the man. He stopped the experiment and told everyone to break for lunch. They were close. Everyone in the room could feel it. The counters were climbing faster with each rod withdrawal. The neutron population was clearly approaching the threshold where the chain reaction would sustain itself. And Fermi just called a lunch break. Some people have speculated about why. Was he being cautious? Did he want everyone sharp and rested for the final steps? Was he just hungry? Knowing Fermi, it was probably all three, but mostly it was about control. He was not going to rush this. He was not going to let excitement or impatience introduce sloppiness into the most important experiment of his life. So they ate lunch. Imagine that. You're on the verge of initiating the first self-sustaining nuclear chain reaction in history, and your boss says, "Let's go have a sandwich." They came back. The pile was sitting there, quiet, inert, waiting, and Fermi resumed exactly where he had left off. More rod withdrawals, a few inches at a time. More counting. More calculations on his slide rule. The clicking of the Geiger counters getting faster. The pen on the chart recorder tracing a line that was curving upward more and more steeply. And here's the thing about what Fermi was watching for. The key signature of a self-sustaining reaction. When the pile was subcritical, meaning K was less than 1, each burst of neutron activity would rise and then level off. The neutron population would find a new equilibrium. But when K equals exactly 1, when each fission event produces on average exactly one more fission event, the neutron population doesn't level off. It just keeps rising, slowly, steadily, without stopping. And if K goes above 1, even slightly, the rise becomes exponential. Not explosive, not in this pile. The delayed neutrons gave them a comfortable margin of response time, but unmistakably exponential. The line on the chart recorder would curve upward and just keep curving. At 3:25 in the afternoon, Fermi ordered the last control rod withdrawn another foot, and the counters started climbing. And they didn't. Stop! The clicking became so rapid it merged into a continuous roar. The chart recorder pen traced a line that swept upward in a smooth, accelerating curve. Fermi watched it. Everyone watched it. And Fermi, with that quiet confidence that defined him, looked at his calculations, looked at the instruments, and announced that the reaction was self-sustaining. The pile had gone critical. He let it run for about 28 minutes. 28 minutes of a controlled, self-sustaining nuclear chain reaction, the first one in human history. The power output was tiny, about half a watt. You couldn't have lit a flashlight with it, but the power level was beside the point. What mattered was that the chain reaction was real, it was controllable, and it behaved exactly the way the physics predicted it would. Fermi could speed it up by withdrawing rods. He could slow it down by inserting them. He could shut it down entirely. The reactor was not a bomb. It was a machine, and it obeyed its operator. Then Fermi ordered the rods reinserted and the pile shut down. And for a moment, the squash court was very quiet. Eugene Wigner, the Hungarian-born physicist who had done crucial theoretical work on reactor design, had brought a bottle of Chianti. He'd been saving it for this moment. They passed it around and drank from paper cups. No toasts, no speeches. Just a bottle of Italian wine shared among people who understood the magnitude of what had just happened. Szilard shook Fermi's hand, and then said something that has echoed through history ever since. He told Fermi that this would go down as a black day in the history of mankind. Think about that. In the moment of triumph, Szilard, the man who had first conceived of the nuclear chain reaction, the man who had pushed harder than anyone to make this moment happen, felt not joy, but dread. He understood, maybe more viscerally than anyone else in that room, what this technology could become. Arthur Compton made a phone call. He called James Conant, the president of Harvard who was serving as a key science administrator for the war effort, and he used a prearranged code. He said, "The Italian navigator has just landed in the New World." Conant asked, "And how did he find the natives?" Compton replied, "Very friendly." That was it. That was how the United States government learned that controlled nuclear fission was a reality. A coded phone call comparing Enrico Fermi to Christopher Columbus. Now, let's talk about what this actually meant in practical terms, because the achievement of CP1 wasn't an endpoint. It was a beginning. And the thing it was beginning was, in many ways, even more extraordinary than the pile itself. The immediate purpose, the reason General Groves cared, the reason the Army was funding all of this, was plutonium. Remember, the bomb program needed fissile material, and there were two paths: enriching natural uranium to get a high concentration of U-235, which was extraordinarily difficult and expensive, or creating an entirely new element, plutonium-239, by bombarding U-238 with neutrons in a reactor. CP1 had just proved that the second path was viable. You could build a reactor, sustain a chain reaction, and in the process, some of the U-238 atoms in the fuel would absorb neutrons and, through a couple of beta decays, transform into plutonium. But CP1 itself was never going to produce meaningful quantities of plutonium. Half a watt of power means an incredibly low neutron flux, which means an incredibly slow rate of plutonium production. To make enough plutonium for a weapon, you needed reactors that operated at millions of watts, megawatts, and that meant solving a whole new set of engineering problems that made CP1 look like a warm-up exercise. And this is where the story shifts from pure physics to industrial engineering on a scale that's hard to comprehend. Because within months of CP1 going critical, the decision was made to build full-scale production reactors. Not in Chicago. You wouldn't want a high-power reactor under a football stadium in the middle of a major city, for reasons that should be obvious. The site chosen was Hanford in southeastern Washington state, along the Columbia River. And the man tasked with designing and building these production reactors was someone we haven't talked about yet, an engineer whose contribution to the nuclear age is arguably as important as Fermi's, even though far fewer. People know his name. His name was Crawford Greenewalt, and he worked for DuPont. Now, DuPont, the chemical company, the people who made nylon and gunpowder and paint, might seem like an odd choice to build nuclear reactors. But Groves specifically wanted an industrial firm with experience managing enormous, complex construction projects, and DuPont fit the bill. They had built massive munitions plants during World War I. They understood large-scale chemical processing. And critically, they had a culture of engineering discipline and safety that Groves trusted. Greenewalt was a chemical engineer, tall, thoughtful, meticulous, the kind of person who asked the right questions and didn't pretend to understand things he didn't. He had actually been present in the squash court on December 2nd. He had watched Fermi's demonstration. And now his job was to take that crude half-watt pile of graphite and uranium bricks and scale it up by a factor of roughly 1,000,000. Think about what that means. Scaling any engineering system by a factor of 1,000,000 introduces problems you cannot predict from the small-scale version. It's like the difference between cooking dinner for 2 people and feeding an army of 2,000,000. The basic chemistry of cooking is the same, but everything else changes. Heat removal, for one. CP1 generated so little heat that it didn't need any cooling system at all. A production reactor running at hundreds of megawatts would generate enormous amounts of heat, enough to melt the uranium fuel, warp the graphite, and destroy the entire structure if you couldn't get rid of it fast enough. That's why Hanford was built on the Columbia River. The reactors would be cooled by river water, pumped through aluminum tubes that ran directly through the reactor core, carrying away the heat and dumping it back into the river. The environmental implications of that were not something anyone was thinking too carefully about in 1943. And that's a whole other story for another time. But there was another problem, one that nobody saw coming, and it nearly derailed the entire plutonium production program. It's one of the great detective stories in engineering history, and it starts with a mysterious phenomenon that had no name yet. When the first Hanford production reactor, called B-reactor, was loaded with fuel and brought to criticality in September 1944, everything seemed to work at first. The reactor went critical, power levels climbed, and the operators began to relax. Then, after several hours of operation, the power started dropping, slowly at first, then faster. The reactor was dying. The chain reaction was sputtering out, as if something invisible was swallowing neutrons right out of the air. And that's essentially what was happening. Something inside the reactor was absorbing neutrons so aggressively that it was choking the chain reaction to death. Now, put yourself in the shoes of the engineers and physicists at Hanford in that moment. You've spent over a year building this enormous facility in the middle of the Washington desert. You've poured concrete, machined thousands of uranium fuel slugs, constructed an elaborate water cooling system, and you've done all of this under wartime secrecy with the pressure of the entire Manhattan Project bearing down on you. And now your reactor just stops working. Nobody knows why. The instruments say the reactor went critical, ran fine for a few hours, and then the reactivity just drained away like water out of a bathtub. By the next morning, the reactor was completely dead. No chain reaction at all. But here's what's strange. After sitting idle for a while, maybe a day or so, the reactor started coming back to life on its own. You could restart it, bring it back to criticality, and it would run again. And then, hours later, the same thing would happen. Power would fade, the chain reaction would die, and you'd be left staring at a billion-dollar pile of graphite and uranium that refused to cooperate. This is where the detective work begins, and it's genuinely one of the most elegant pieces of scientific troubleshooting in the 20th century. The physicists at Hanford, working closely with Fermi and others back at Chicago, realized that the problem had to be a fission product. When uranium atoms split, they don't just release neutrons and energy. They also produce a whole zoo of smaller atoms, the fragments of the original uranium nucleus. These fission products are themselves often radioactive and unstable, and they decay through chains of other elements. Most of these fission products are harmless from a reactor operation standpoint. They exist. They're radioactive, but they don't absorb enough neutrons to matter. But what if one of them was an extraordinarily powerful neutron absorber? What if one particular fission product was being created during operation, building up in concentration, and eating neutrons so voraciously that it could shut down the entire chain reaction? That's exactly what was happening. The culprit turned out to be xenon-135, a specific isotope of the noble gas xenon. And when I say it's a powerful neutron absorber, I need you to understand just how extreme this is. Xenon-135 has the largest thermal neutron absorption cross-section of any known nuclide. Its cross-section, which is essentially a measure of how likely it is to capture a passing neutron, is about 2.6 million barns. Now, that number won't mean much unless I give you some context. A typical uranium-235 atom, the fissile fuel itself, has an absorption cross-section of around 680 barns. So xenon-135 is nearly 4,000 times more likely to grab a neutron than the very fuel you're trying to sustain a chain reaction with. It's like trying to run a business where one employee is intercepting almost every customer before they can reach the front desk. Even a tiny amount of xenon-135 can have an outsized effect on reactor behavior. Here's how the poisoning cycle works, and it's beautifully logical once you see it. When uranium fissions, one of the many possible fission products is iodine-135. Iodine-135 is radioactive, and it decays with a half-life of about 6.5 hours into xenon-135. So during reactor operation, iodine-135 is being produced continuously and steadily converting into xenon-135. Now, while the reactor is running at high power, some of that xenon-135 is being destroyed. It absorbs a neutron and transmutes into xenon-136, which is stable and harmless. So, you reach a kind of equilibrium. Xenon is being created from iodine decay and destroyed by neutron absorption, and these two processes roughly balance each other out. The reactor can handle this steady-state level of xenon. But here's the kicker. If you reduce power or shut the reactor down, you stop destroying xenon-135 because there are no longer enough neutrons flying around to burn it away. But the iodine-135 that's already built up in the fuel doesn't care that you've shut down. It keeps decaying into xenon-135 on its same 6.5-hour schedule. So after shutdown, the xenon concentration actually increases. It peaks roughly 10 to 11 hours after shutdown, and at that peak, the xenon load can be so enormous that the reactor literally cannot restart. You don't have enough excess reactivity to overcome the neutron-absorbing blanket of xenon that's smothering your core. Then, gradually, the xenon-135 itself decays. It has a half-life of about 9 hours, into cesium-135, which is a much weaker absorber. So after a day or so, the xenon has decayed away enough that you can restart the reactor, and the whole cycle begins again. This is what the Hanford engineers were seeing. That mysterious rise and fall, the reactor dying and then resurrecting itself. It was all xenon-135, building up and decaying away in this rhythmic, predictable pattern. Once they understood the mechanism, the question became, how do you fix it? And this is where a decision made months earlier, almost on a hunch, saved the entire program. When DuPont's engineers were designing the B reactor, they had planned for a core with 1,500 fuel channels, tubes running through the graphite where uranium slugs would be loaded. The physicists at Chicago, led by Fermi and Eugene Wigner, had calculated that 1,500 channels would be sufficient to sustain a chain reaction and produce plutonium at the required rate. But DuPont's chief design engineer, George Graves, and the broader DuPont team, particularly Crawford Greenewalt, who'd been deeply involved since witnessing CP1, insisted on adding extra fuel channels. They pushed the design to 2,004 channels. The physicists thought this was unnecessary, even wasteful. There were arguments about it. The DuPont engineers were accused of being overly conservative, of not trusting the physics, but DuPont had a deep institutional culture of building in engineering margins. They'd spent decades designing chemical plants where unexpected problems were the norm, not the exception. And their philosophy was simple. If you can add margin, because something will go wrong that you didn't anticipate. That conservative instinct turned out to be prophetic. Those extra 500 fuel channels provided exactly the additional reactivity needed to overcome xenon poisoning. By loading uranium into the spare channels, the operators could push the reactor's total reactivity high enough to burn through the xenon 135 and maintain the chain reaction even at equilibrium xenon levels. Without those extra channels, the B reactor might have been a very expensive failure. The entire Hanford plutonium production timeline could have been thrown off by months while engineers redesigned and rebuilt the core. In wartime, months mattered enormously. There's a lesson in this that goes way beyond nuclear engineering, and it's worth sitting with for a moment. The physicists had done brilliant theoretical work. Their calculations were correct for the parameters they knew about. But xenon poisoning was what engineers sometimes call an unknown unknown, a problem that doesn't exist in your model because you don't even know the phenomenon is possible until you encounter it at scale. This is exactly the kind of thing that separates small-scale experiments from full-scale engineering. CP1 ran at half a watt. At that power level, the amount of xenon 135 produced was so vanishingly small that it had no measurable effect. You'd never see it. It was invisible. Only when you scaled up to megawatt levels, producing enormous quantities of fission products, did xenon poisoning emerge as a showstopper. And the only thing that saved the program was an engineer's instinct to build in margin for problems that hadn't been imagined yet. Once the xenon problem was understood and overcome, Hanford's reactors began producing plutonium in earnest. The B reactor was followed by the D reactor and the F reactor, all along the Columbia River, all using the same basic water-cooled, graphite-moderated design. The plutonium they produced was chemically separated from the irradiated uranium fuel in massive processing canyons, the T plant and the B plant, using a bismuth phosphate process that had been developed at the metallurgical laboratory in Chicago. The separated plutonium was shipped to Los Alamos, New Mexico, where a different team of physicists and engineers was working on the problem of actually building a weapon. And here's where the story of the reactor connects to a much larger and darker chapter of history. The plutonium produced at Hanford went into the Trinity test device, detonated on July 16, 1945, in the New Mexico desert, and into the Fat Man bomb dropped on Nagasaki on August 9, 1945. The uranium bomb, Little Boy, dropped on Hiroshima 3 days earlier, used a completely different fissile material, uranium-235, enriched through an agonizing industrial process at Oak Ridge, Tennessee. But the plutonium path, the one that began with Fermi's quiet experiment under the squash court, stands. The one that ran through Hanford's massive production reactors and DuPont's chemical separation plants. That path ended at Nagasaki. It's impossible to talk about the birth of nuclear reactors without reckoning with this. Fermi's pile was a scientific triumph, one of the great intellectual achievements of the century. But its immediate purpose was to enable the production of material for a weapon of unprecedented destructive power. The people involved knew this. Szilard's dark comment on December 2, 1942, that it would be a black day in the history of mankind, reflected an awareness that was present from the very beginning. These were not naive people. Many of them, Fermi included, were refugees from fascism who understood exactly what was at stake in the war. The moral calculus they performed, or avoided performing, is something historians and ethicists have been debating ever since. But the story doesn't end with the bombs. In fact, in many ways, the story of nuclear reactors only truly begins after the war, because the same basic physics that produced plutonium for weapons could also be harnessed to produce something else entirely: electricity. And the person who first seriously pushed the idea of nuclear power for civilian use was someone we haven't talked about yet, a naval officer with an engineering degree and an almost terrifying force of will. His name was Hyman Rickover, and he was about to take everything that Fermi and the Manhattan Project had built and turn it into something entirely new. Rickover was not a physicist. He wasn't a theorist. He wasn't someone who spent late nights scribbling equations on a chalkboard. He was, by every account, one of the most difficult, abrasive, demanding human beings the United States Navy had ever produced. And that's saying something, because the Navy has produced some real characters. Born in 1900 in a small town in what's now Poland, he emigrated to the United States as a child, grew up in Chicago. Funny how Chicago keeps showing up in this story. And graduated from the Naval Academy in 1922. For the next 2 decades, he was a career naval officer, competent but not particularly distinguished, working his way through various engineering assignments on submarines and surface ships. He was brilliant, no question, but he was also the kind of person who made enemies everywhere he went, because he had zero tolerance for inefficiency, zero patience for bureaucracy, and absolutely no interest in being polite about it. During the war, Rickover served in the Bureau of Ships, managing electrical systems. Not glamorous work, not the kind of assignment that gets you medals or promotions, but it gave him something invaluable, a deep, practical understanding of how the Navy actually built and maintained complex machinery. He understood procurement. He understood quality control. He understood the difference between a system that works on paper and a system that works in the middle of the North Atlantic in January. And in 1946, the Navy sent him to Oak Ridge, Tennessee, to study nuclear technology as part of a small group of officers and engineers. This was supposed to be an educational program, a way for the military to understand what this new nuclear capability might mean for the future. Most of the officers who went through the program came away impressed, but uncertain about practical applications. Rickover came away with a vision that would consume the rest of his career. Here's what Rickover saw that others didn't, or at least didn't see as clearly. A nuclear reactor doesn't need air. Think about what that means for a submarine. A conventional submarine in the 1940s ran on diesel engines on the surface and battery power when submerged. The diesel engines needed air, huge amounts of air, so the sub had to surface regularly to run its engines and recharge its batteries. Underwater, on battery alone, a submarine was slow and limited. It could stay submerged for maybe a day or two at most before it had to come back up. This made submarines vulnerable. During the war, Allied anti-submarine warfare had become devastatingly effective precisely because submarines had to surface. But a nuclear-powered submarine? It would never need to surface for fuel or air for its engines. It could stay underwater for months. It could cruise at high speed continuously, not just in short bursts. It would be, in the truest sense of the word, a real submarine. A vessel that actually lived beneath the waves rather than just visiting. Rickover became obsessed with making this happen. And when I say obsessed, I mean he reorganized his entire existence around this single goal. He fought the Navy bureaucracy with a ferocity that's genuinely hard to overstate. The Navy's traditional promotion system didn't reward people like Rickover. He was passed over for Rear Admiral twice, which normally would have forced his retirement. He survived only because Congress intervened, because by that point he had powerful allies on Capitol Hill who recognized what he was trying to do. He built a unique dual-hatted organization, serving simultaneously as head of the Naval Reactors branch within the Atomic Energy Commission and as head of the Nuclear Propulsion Program within the Navy. This gave him extraordinary autonomy. he reported to two masters, which in practice meant he could play them against each other and answer to neither. But here's the thing. Rickover's genius wasn't just political maneuvering. It was engineering judgment. He had to make a fundamental design choice early on, and the choice he made shaped the entire future of nuclear power, not just for the Navy, but for the civilian world too. The question was simple. What kind of reactor do you put in a submarine? The Manhattan Project reactors, CP1, the Hanford production reactors, used graphite as a moderator, remember? Graphite slows down the neutrons, so they're more likely to cause fission in uranium-235. But graphite reactors are big. They're bulky. You need tons and tons of graphite to moderate the neutrons effectively. That's fine if you're building a massive production facility on the banks of the Columbia River. But it's completely impractical for a submarine where every cubic foot matters. Rickover chose water. Specifically, pressurized light water, ordinary H2O, but kept under enormous pressure so it wouldn't boil even at extremely high temperatures. Water is actually a decent neutron moderator. Hydrogen atoms are almost exactly the same mass as neutrons, so when a neutron collides with a hydrogen nucleus, it transfers a lot of its energy in a single collision, like a billiard ball hitting another billiard ball of the same weight. You get efficient slowing with much less material than graphite requires, and water has another advantage. It can also serve as the coolant, carrying heat away from the reactor core. So you get moderation and cooling in a single substance. Elegant, compact, practical. The trade-off is that you need enriched uranium. Natural uranium, the kind Fermi used in CP1, is only about 0.7% uranium-235. In a graphite-moderated reactor, that's enough to sustain a chain reaction, because graphite is a very efficient moderator that absorbs relatively few neutrons. But water absorbs more neutrons than graphite does. So to make a water-moderated reactor work, you need fuel that's enriched to several percent uranium-235 or higher, fuel with a higher concentration of the fissile isotope to compensate for the neutrons lost to absorption by the water. During the Manhattan Project, enriching uranium had been one of the most expensive and difficult parts of the entire enterprise. But Rickover had the weight of the military behind him, and by the late 1940s, the enrichment infrastructure at Oak Ridge was available for this new purpose. Rickover contracted with Westinghouse to build the reactor plant. He drove the engineers there mercilessly. He personally reviewed design details that most program managers would have delegated 3 levels down. He would show up at contractor facilities unannounced, quiz junior engineers on their calculations, and if he found sloppy work, the consequences were severe and immediate. People who worked for Rickover either loved him or hated him, often both at the same time. He created a culture of technical excellence that was, frankly, unlike anything else in the military-industrial complex. Every weld was inspected, every procedure was documented, every operator was trained to his exacting standards. He personally interviewed every officer who would serve on a nuclear submarine, and these interviews were legendary. Hours-long ordeals designed to test not just technical knowledge, but character, judgment, and the ability to think under pressure. The first prototype reactor, called S-1W, was built not in a submarine but in a landlocked facility in the Idaho desert, the National Reactor Testing Station, now called Idaho National Laboratory. They actually constructed a complete submarine hull section, buried it in the ground, and installed the reactor inside it, so they could test the entire propulsion system under realistic conditions. This prototype went critical in 1953, and it worked. It worked beautifully. The reactor heated pressurized water in a primary loop. That hot water transferred its heat through a steam generator to a secondary loop of water that wasn't radioactive. The secondary water boiled into steam. The steam drove turbines, and the turbines turned the propeller shaft. It's essentially the same principle as a coal-fired power plant, except instead of burning coal to make heat, you're splitting atoms. And then came the USS Nautilus. Launched in January 1954, commissioned in September of that year, it was the world's first nuclear-powered submarine. On its initial sea trials, it transmitted the famous message, "Underway on nuclear power." Those 4 words changed naval warfare forever. The Nautilus could do things no submarine had ever done. In 1958, it made the first submerged transit of the North Pole, traveling under the Arctic ice cap, a voyage that would have been utterly impossible for a diesel-electric submarine. It could sprint at over 20 knots underwater for as long as its food supplies lasted. The limiting factor on patrol length was no longer fuel or battery life. It was how much food you could store and how long the crew could endure being sealed in a metal tube. Now, here's where Rickover's submarine program connects back to the broader story of nuclear energy, because the pressurized water reactor design that Rickover chose for the Navy became the basis for most of the world's civilian nuclear power plants. This wasn't inevitable. There were other reactor designs: gas-cooled reactors, heavy water reactors, sodium-cooled fast reactors, molten salt reactors. Some of these had real technical advantages, but Rickover's program had done something that none of the alternative designs could match. It had actually built a working reactor, tested it exhaustively, and operated it safely at sea. When the Eisenhower administration launched the Atoms for Peace program in the mid-1950s, pushing for civilian nuclear power as a counterweight to the military's monopoly on atomic energy, the fastest path to a working power plant was to scale up what Rickover had already proven. The first commercial nuclear power plant in the United States was Shippingport Atomic Power Station in Pennsylvania, and it was essentially a scaled-up version of a naval reactor. It went critical in December 1957, and Rickover personally oversaw its construction and startup. Because of course he did. The reactor was a pressurized water design built by Westinghouse, using enriched uranium fuel with the same basic 2-loop system: pressurized water in the primary loop absorbing heat from the core, transferring that heat to a secondary loop to make steam. Steam driving turbines connected to electrical generators. The same fundamental architecture that powered the Nautilus was now generating electricity for the grid. And this is how a design choice made for a very specific military application. Compactness, reliability, the need to work inside a submarine hull, ended up defining the civilian nuclear power industry for decades. Most of the nuclear power plants operating in the world today are either pressurized water reactors or their close cousin, the boiling water reactor, which is a simplification where you skip the secondary loop and let the water boil directly in the reactor core. Both are light water reactors. Both trace their lineage back, in one way or another, to the choices Rickover made in the late 1940s. There's something almost accidental about this. The pressurized water reactor isn't necessarily the best design for generating electricity. It operates at relatively high pressure, which means thick, expensive pressure vessels and piping. It requires enriched uranium, which adds cost and proliferation concerns. Other designs might be more efficient, might produce less waste, might be inherently safer. But Rickover's design had the one advantage that mattered most in the 1950s. It existed. It worked. It had a track record. And in engineering, a proven design that's good enough will almost always beat a theoretically superior design that's still on the drawing board. Engineers sometimes call this path dependence, the idea that early choices constrain later ones, that the first technology to achieve practical success tends to lock in its dominance, even if alternatives might eventually prove better. So by the late 1950s and into the 1960s, nuclear power was scaling up rapidly. Utilities were ordering reactors. Westinghouse and General Electric were competing for contracts. The Atomic Energy Commission was promoting nuclear power as the energy source of the future. Electricity too cheap to meter, as the famous phrase went, though that promise was always more aspirational than realistic. And the basic physics underlying all of it, every single one of these reactors, was still the same physics that Fermi had demonstrated under the stands of Stagg Field. Neutrons hitting uranium nuclei, fission releasing energy and more neutrons. A chain reaction sustained and controlled by carefully balancing the neutron economy. The scale had changed enormously, from half a watt to hundreds of megawatts. But the fundamental principle hadn't changed at all. What had changed, though, was the complexity of the engineering required to manage that principle safely at industrial scale. And this is where the story takes a darker turn, because the history of civilian nuclear power is not just a story of triumph and progress. It's also a story of accidents, miscalculations, and lessons learned at terrible cost. And to understand that part of the story, you need to understand something about how these reactors behave when things go wrong. Not just when everything is running smoothly, but when the unexpected happens. When operators make mistakes, when equipment fails in ways nobody anticipated. Let's start with something that might seem counterintuitive. A nuclear reactor, in many ways, wants to be stable. Remember how Fermi's pile worked? You pull out a control rod, reactivity increases, the chain reaction intensifies, the reactor heats up. But in a well-designed reactor, that heating itself tends to slow the reaction down. This is called a negative temperature coefficient of reactivity, and it's one of the most important safety features in reactor design. Here's why it works. As the fuel and the moderator heat up, the uranium atoms and the water molecules are vibrating more energetically, and this changes the way neutrons interact with them. In a light water reactor specifically, as the water heats up, it becomes less dense, which means it's less effective as a moderator, which means fewer neutrons are slowed down to the right speed for fission, which means the chain reaction naturally dials itself back. It's a beautiful piece of self-regulating physics. The reactor pushes back against its own power increases. Fermi would have appreciated the elegance of it. But here's the thing. Not all reactor designs have this property to the same degree. And some designs, under certain conditions, can behave in exactly the opposite way. They can have a positive void coefficient, meaning that when the coolant boils and forms steam voids, the reactivity actually increases. The reactor doesn't push back, it pushes forward, it accelerates, and that difference, that seemingly technical distinction about coefficients and void fractions, is at the heart of the worst nuclear accident in history. On April 26, 1986, operators at the Chernobyl nuclear power plant in northern Ukraine, then part of the Soviet Union, were conducting a safety test on Unit 4. The reactor was an RBMK design, which stands for a Russian acronym meaning High Power Channel Reactor. It was a very different beast from Rickover's pressurized water reactors. The RBMK used graphite as its moderator, like Fermi's original pile, but used water as its coolant, flowing through individual pressure tubes rather than filling a single large pressure vessel. This design had certain advantages. You could build it without the massive forged pressure vessels that Western reactors required, and you could refuel it while it was still running. But it also had that dangerous characteristic. Under certain operating conditions, particularly at low power, it had a positive void coefficient. If the cooling water started to boil, the graphite was still there moderating neutrons, but the water, which also absorbed some neutrons, was turning to steam and becoming less effective as an absorber. So, you'd get more reactivity, not less. More power, more boiling, more reactivity, a feedback loop running in the wrong direction. The operators that night were trying to test whether the spinning turbine, after being disconnected from the steam supply, could generate enough electricity during its coast down to power the emergency cooling pumps for the 40 or so seconds it would take for the backup diesel generators to start. It was a legitimate safety question, but to conduct the test, they had to operate the reactor at low power, and they had to disable several safety systems that would have automatically shut the reactor down. They were essentially driving with the airbags disconnected, the seatbelt off, and the brakes partially disabled on a road they'd never driven before, at night. The sequence of events is complicated, and there's been decades of debate about how much blame falls on the operators versus the reactor design versus the institutional culture that allowed such a test to proceed under such conditions. But the basic physics is this. The reactor ended up in an unstable, low-power state, with most of its control rods withdrawn. When the operators initiated the test and the coolant flow decreased, the water began to boil. In a Western pressurized water reactor, this would have reduced reactivity. In the RBMK, it increased it. Power surged. The operators hit the emergency shutdown button, the one they called AZ5, which was supposed to drive all the control rods back into the core. But here's where another design flaw became catastrophic. The RBMK control rods had graphite tips at their lower ends, and when these rods were almost fully withdrawn and then reinserted, those graphite tips entered the core first, briefly displacing water in the control rod channels. Graphite is a moderator, so for a few seconds, inserting the emergency shutdown rods actually increased reactivity in the lower part of the core instead of decreasing it. The power spike was almost instantaneous. The reactor went from about 200 megawatts thermal to something on the order of 30,000 megawatts in a matter of seconds, maybe more. The fuel shattered. Steam pressure blew the 1,000-ton reactor lid off the building. A second explosion, likely a steam explosion, though some researchers have argued it may have involved hydrogen, tore the reactor apart and scattered burning graphite and reactor fuel across the plant site. 2 plant workers died that night from the explosions. Over the following days and weeks, firefighters and emergency workers received enormous radiation doses fighting the graphite fires and attempting to contain the disaster. 28 of them died from acute radiation syndrome within months. The eventual total death toll is debated to this day. Estimates range from a few thousand to tens of thousands of excess cancer deaths over the decades that followed, depending on the methodology and the assumptions used. What's not debated is that it was a catastrophe, the worst nuclear accident the world has ever seen, and it shook public confidence in nuclear power to its foundations. And yet, and this is important, the Chernobyl disaster was not a failure of nuclear physics. The physics worked exactly as the physics always works. Neutrons hit uranium, fission occurs, energy is released. The chain reaction obeys the same rules Fermi demonstrated in 1942. What failed was the engineering, the design choices, the safety culture, the institutional framework. The RBMK had known design vulnerabilities that had not been adequately addressed. The operators were inadequately trained for the specific scenario they encountered. The safety test procedures were poorly planned and poorly supervised. Multiple layers of protection were deliberately bypassed. It was a systems failure, a human failure, wrapped around physics that was doing exactly what physics does. 3 years later, in a very different setting, something happened that tells the other side of the story. On March 28, 1979. Actually, this was 7 years before Chernobyl. Let me get my timeline right. 3 Mile Island in Pennsylvania experienced a partial meltdown of its Unit 2 reactor. This was a pressurized water reactor, a direct descendant of Rickover's naval design. A stuck-open valve allowed coolant to drain from the reactor. The operators, confused by misleading instrument readings, made the situation worse by reducing emergency cooling water flow when they should have been increasing it. About half the core melted. It was terrifying. It was a serious accident. But here's what's remarkable. The thick steel and concrete containment building, the kind of structure that Western reactor designs required and that the RBMK at Chernobyl notably lacked, held. The radioactive release to the environment was minimal. No one died. No one was injured. The health effects on the surrounding population, according to every major study conducted since, were negligible. The reactor was destroyed. The cleanup took 14 years and cost about $1 billion, and the accident devastated the American nuclear industry's growth. But the containment worked. The defense-in-depth philosophy that Western reactor designers had insisted on, multiple independent barriers between the radioactive fuel and the outside world, did what it was supposed to do even when the operators and the equipment failed. Think about what that means. 2 accidents, both involving the same fundamental physics, both involving operator error and equipment failure, but radically different outcomes because of engineering design choices. One reactor had a positive void coefficient and no containment building. The other had a negative temperature coefficient and robust containment. Those design choices were made years, even decades, before the accidents occurred. The engineers who insisted on containment buildings, who demanded negative reactivity coefficients, who built in redundant safety systems, they were making decisions whose consequences wouldn't be fully apparent for a generation. That's what engineering really is when you think about it. It's making choices today that protect people tomorrow, people you'll never meet, in scenarios you hope will never happen. And then there's Fukushima, March 11th, 2011, a magnitude 9.0 earthquake off the coast of Japan, followed by a massive tsunami. The Fukushima Daiichi nuclear power plant had 6 boiling water reactors, another design that traces its lineage back through General Electric to the same basic light water technology that Rickover championed. The reactors actually survived the earthquake. The control rods inserted automatically. The chain reactions stopped. But stopping the chain reaction doesn't stop the heat. This is something we touched on earlier. Decay heat. From the radioactive decay of fission products in the fuel. Even after shutdown, a large reactor produces tens of megawatts of thermal energy, and that heat has to be removed or the fuel will overheat and melt. The tsunami knocked out the backup diesel generators that powered the emergency cooling systems. The batteries lasted about 8 hours, and then, with no way to circulate cooling water, 3 of the 6 reactors suffered meltdowns over the following days. Hydrogen explosions blew apart the reactor buildings. Radioactive material was released into the atmosphere and the ocean. Nearly 160,000 people were evacuated from the surrounding area. It was a disaster, the second worst nuclear accident in history. But again, and I keep coming back to this because it matters, the physics wasn't the surprise. Decay heat was well understood. The need for continuous cooling after shutdown was well understood. What failed was the planning for extreme natural events. The tsunami walls were designed for a wave that turned out to be far smaller than the one that actually hit. The backup generators were located in basements that flooded. The engineers had underestimated the threat, not because they were careless, but because the historical record they relied on didn't go back far enough to capture the true range of what nature could throw at them. Every one of these accidents led to changes. 3 Mile Island led to massive improvements in operator training, control room design, and emergency procedures across the global nuclear industry. Chernobyl led to the end of the RBMK design's expansion and to new international safety cooperation frameworks. Fukushima led to reassessments of natural hazard risks at nuclear plants worldwide, to new requirements for backup power and cooling that don't depend on external electricity. The lessons were paid for dearly, but they were learned. And now, here we are. It's the 21st century, and the conversation about nuclear power is shifting again. Climate change has reframed the equation. Whatever you think about nuclear power's risks, it produces electricity with virtually no carbon dioxide emissions. A single uranium fuel pellet, about the size of the tip of your little finger, contains as much energy as a ton of coal. The entire amount of nuclear waste produced by a reactor in a year can fit in the back of a pickup truck. Contrast that with the millions of tons of carbon dioxide that a coal plant of similar output pumps into the atmosphere every year. New reactor designs are being developed that are smaller, simpler, and incorporate what engineers call passive safety. They use natural forces like gravity and convection to keep the reactor safe, even if every pump and every operator fails. Some of these designs can't melt down, not because of engineered safety systems, but because of the fundamental physics of how they operate. Fermi would find that deeply satisfying, I think. The idea that you could design a reactor where the physics itself prevents catastrophe, where the neutron economy self-regulates so completely that a runaway chain reaction is physically impossible. And that brings us all the way back, doesn't it? Back to a squash court under the west stands of Stagg Field on a cold December afternoon in 1942. A man standing on a balcony, watching a pen trace a line on a chart recorder, knowing that what he's seeing has never happened before in the history of the world. A controlled, self-sustaining nuclear chain reaction. 49 people in that room, watching the birth of something that would reshape civilization. Fermi, calm as ever, doing the math in his head, knowing exactly what the instruments would show before they showed it. Wigner pulling out a bottle of Chianti. No labels on the bottle, no toasts, just paper cups passed around in quiet celebration. Fermi went on to contribute to the Manhattan Project at Los Alamos, then returned to academic physics at the University of Chicago after the war. He died young, in 1954, of stomach cancer. He was 53. Element 100, fermium, is named after him. So is the Fermi National Accelerator Laboratory, Fermilab, just west of Chicago. His legacy is everywhere. In the reactors that generate about 10% of the world's electricity, in the physics that underpins our understanding of the atom, in the methodology of careful, systematic experimentation that he modeled for generations of scientists. But maybe the most important thing Fermi demonstrated that day wasn't the chain reaction itself. It was the idea that you could understand something powerful enough to destroy a city, and instead of being overwhelmed by it, you could control it. You could measure it, predict it, manage it. You could slide the control rod in, and the reaction would stop. You could pull it out, and the reaction would resume. The universe obeyed rules. And if you understood those rules deeply enough, you could work with forces that would otherwise be unimaginably dangerous. That's the promise of engineering, really. Not that we can eliminate risk. We can't. And the history of nuclear power proves that painfully. But that we can understand it, quantify it, and make informed choices about it. So as you lie there tonight, wherever you are, think about this. The same physics that powers the stars, that fuses hydrogen in the core of the sun, is a cousin of the physics that Fermi harnessed in that pile of graphite and uranium. The same neutrons, the same nuclear forces, the same fundamental interactions that have been running since the first moments after the Big Bang, and a quiet, methodical Italian physicist working in a converted squash court in Chicago figured out how to hold that fire in his hands, not with brute force, but with understanding, with careful measurement and patient calculation, with slide rules and cadmium strips and a pile of black bricks stacked by hand. That's a good thought to drift off to, I think. The idea that understanding is itself a kind of safety, that knowledge, carefully applied, can tame even the most powerful forces in nature. That somewhere in the chain of discovery that stretches from Becquerel's photographic plates to Rutherford's gold foil, to Fermi's pile, to the reactor that might be humming quietly right now at a power plant 100 miles from where you're lying. Somewhere in that chain, there's a thread of human curiosity and human ingenuity that never broke. It bent, it frayed. It was tested by tragedy and failure, but it held. It's still holding. And tonight, that's enough. Let that thought settle. Let it go quiet and rest.